Today, we're diving into a material that's quietly revolutionizing everything from green energy to medical sensors, proton-conducting polymers.
That sounds specific. What exactly are they, and why are they so important?
Think of them as specialized plastic films that act like superhighways for protons, the tiny positively charged hearts of hydrogen atoms. This unique ability is unlocking next-generation technologies across many fields.
Okay, a proton highway. Where is the first stop on this technological road trip?
Our first stop is high-temperature fuel cells, or HTMFCs. These devices create electricity from hydrogen and oxygen, and operating them at higher temperatures makes them more efficient and durable.
But I imagine keeping a polymer stable and conductive at high temperatures with low humidity is a huge challenge, right?
Exactly, and that's where the innovation comes in. Researchers are designing new polymers, like sulfonated polyphenylene, that have densely packed acid groups, creating pathways for protons to hop, even with very little water around.
So they're building the proton highway to be effective even in a drought. What about getting the fuel, the oxygen, to where it needs to go?
Great question. That's the job of highly oxygen-permeable ionomers, or HOPEs. These are mixed in with the catalyst and are designed to have a high oxygen solubility, ensuring the catalyst doesn't get starved of oxygen, which boosts performance significantly.
So it's a two-part solution. One polymer for the main membrane and another specialized one mixed with the catalyst. It's incredibly clever.
This summary table really lays it all out. For each application, it lists the required properties, like high conductivity and stability, alongside the current challenges we're trying to solve, like cost and long-term durability.
I see fuel cells have specific targets set by organizations like Nagao, aiming to get the membrane thickness down to just a few micrometers. That's incredibly thin.
Now, if a fuel cell combines hydrogen and oxygen to make water and electricity, what happens if you run that process in reverse?
You'd use electricity and water to produce hydrogen and oxygen. That's a water electrolyzer, a key technology for producing green hydrogen.
Precisely. And proton-conducting polymers are the heart of polymer electrolyte membrane, water electrolyzers or PEMs. They provide the medium for protons to travel from the anode, where water is split, to the cathode, where hydrogen is formed.
Are researchers still using the same polymers as in fuel cells, like the well-known Nafion?
While Nafion is a benchmark, new materials like sulfonated polyarylene ether sulfone, or SPAs, are showing even better performance. They can be more durable and efficient, pushing us closer to cost-effective green hydrogen production.
It's amazing how tuning the polymer structure can lead to such big performance gains. What about combining this with sunlight?
That's the frontier of photoelectrochemical water splitting. Here, the polymers are coated onto photoanodes that capture sunlight. The polymer's job is to pull water vapor from the ambient air and efficiently transport the protons generated by the light-driven reaction.
So you could potentially generate hydrogen directly from sunlight and humidity. That feels like science fiction. Let's switch gears a bit. What about storing energy?
Proton-conducting polymers are making waves in secondary or rechargeable batteries too. A fascinating example is an all-polymer battery that uses a solid-state organic hydride polymer to store and release hydrogen, acting as the negative electrode.
An all-solid-state battery that runs on protons? That must be much safer than traditional lithium-ion batteries that have flammable liquid electrolytes.
It certainly has that potential for improved safety. Another innovation is using coordination polymer glass. It's a solid but amorphous material, which eliminates the grain boundaries that usually impede ion flow in crystalline solids, resulting in a stable, solid-state proton battery.
Okay, so that covers batteries. What about their cousins, supercapacitors, which deliver quick bursts of power?
In supercapacitors, these polymers are being used in a novel way, as binders in the electrodes. Unlike conventional binders, a proton-conducting binder like Nafion creates fast lanes for ions to reach the electrode surface, dramatically boosting charge and discharge rates.
So the binder is no longer just passive glue, it's an active component of the device.
And for extreme conditions, researchers have developed anti-freezing hydrogel electrolytes based on these polymers. They can maintain high proton conductivity even at temperatures as low as minus 50 degrees Celsius, which is critical for applications in cold climates.
That's incredible. Moving to larger-scale energy storage, I know a major issue with vanadium redox flow batteries is crossover, where the vanadium ions leak through the membrane, causing the battery to lose capacity.
You've hit on the key problem. To solve this, scientists are designing membranes with intrinsic microporosity. These polymers have tiny, rigid pores that are big enough for small protons to pass through, but too small for the bulky vanadium ions, effectively acting like a molecular sieve.
So it's all about creating a selective barrier. It seems like the main theme is always about precisely controlling the transport of specific ions.
Let's move to something completely different: actuators. These are materials that change shape in response to a stimulus.
You mean like artificial muscles for soft robots?
By sandwiching a proton-conducting polymer film between two metal electrodes, you create an ionic polymer metal composite, or IPMC. Applying a low voltage causes ions and water molecules to migrate, making the strip bend and flex. And finally, how are these polymers used in sensors?
Their conductivity is highly sensitive to their environment. For instance, a sensor made with a hydrophilic polymer can detect trace amounts of ammonia in human breath. The ammonia dissolves into the hydrated polymer, gets protonated, and creates more charge carriers, causing a measurable drop in resistance.
So it's a non-invasive way to diagnose medical conditions. What a versatile material. This review covers so many breakthroughs since 2018, showing a clear path forward.
Looking at all this, the future for proton-conducting polymers seems incredibly bright.
It really is. The focus is on advanced molecular design for specific functions, using sustainable materials, and making them cost-effective for commercial use. By collaborating across disciplines, these polymers will continue to be at the heart of our transition to a more sustainable, high-tech world.